Hi everyone, welcome back. In the previous video, we went through the first part of Andre's video. And in this video, Andre gave us the motivation for this lecture. This lecture is meant to give us a deep dive into how we can recreate a transformer with respect to attention is all you need. So this this video includes not just the architecture of the transformer, but it also went through the training of how we pass a corpus of data, a corpus of text through this transformer so that it can start to understand the English language and also start doing some tasks. So in the previous video, we went through the introduction. We also read and explored the data in Andre's Python notebook, and we touched how he used a simple tokenization strategy, the character level tokenization. It's a simplification of the actual byte pair encoding that is typically used for production level models. But for the sake of learning, I think it's fine. Byte pair encoding is meant to reduce the size of the dimension for after we encode a long corpus of text into a vector of numbers. So the idea is, instead of having each character being tokenized into one word, instead why not tokenize it such that all the common words, they can be tokenized into one number, one ID, and for those non-common words, then we can tokenize it into two separate subword tokens. So one very simple example is boy and boys. Boy is really common in text, and boys with the plural might not be as common. So boys would be tokenized to boy plus s, and for the simple word boy, it would just be a single token. But in summary, I guess we'll touch that in another video. I digressed. And finally, in the previous video, we went through the data loader as well. So we loaded the data, and afterwards we batched the chunks of data such that we pass a batch of training examples to the model. In this video, Andre also mentioned how we sample sequences of words in the text instead of just passing the entire corpus of text to train. And I personally found that pretty interesting. And he also went through how in the training, we pass the samples such that when we want the model to be trained on knowing what token they should generate for the third word, let's say, maybe the third token, then in this case, the model can only have access to the first and the second token. They cannot see what comes in the future, which makes sense because how we humans typically speak or write is with respect to what words we have mentioned in the past. So that kind of works. So in the next step, in this video, we'll be continuing from simplest baseline, and in this case, Andre shared a simple classical machine learning model called the bigram. So the bigram is a simple model that predicts the probability of the next word given the word before it. So bigram, in a sense, like we predict words based on the assumption that the word for the next word only depends on the previous word. Of course, there's the trigram where you predict the word based on two words before, the quadgram, I guess, but the idea is there. So Andre will be continuing with this. He'll be sharing the baseline and how this model, the transformer model, will improve based on that. So with that,
okay,
let's get started.
So now that we have our batch of input that we'd like to feed into a transformer, let's start basically feeding this into neural networks. Now, we're going to start off with the simplest possible neural network, which in the case of language modeling, in my opinion, is the bigram language model. And we've covered the bigram language model in my Make More series in a lot of depth. And so here I'm going to sort of go faster, and let's just implement the PyTorch module directly that implements the bigram language model. So I'm importing the PyTorch NN module for reproducibility. And then here I'm constructing a bigram language model, which is a subclass of NN module. And then I'm calling it, and I'm passing it the inputs and the targets. And I'm just printing. Now, when the inputs and targets come here, you see that I'm just taking the index, the inputs x here, which I renamed to idx, and I'm just passing them into this token embedding table. So what's going on here is that here in the constructor, we are creating a token embedding table, and it is of size vocab size by vocab size. And we're using nn.embedding, which is a very thin wrapper around basically a tensor of shape vocab size by vocab size. And what's happening here is that when we pass idx here, every single integer in our input is going to refer to this embedding table and is going to pluck out a row of that embedding table corresponding to its index. So 24 here will go into the embedding table and will pluck out the 24th row. And then 43 will go here and pluck out the 43rd row, etc. And then PyTorch is going to arrange all of this into a batch by time by channel tensor. In this case, batch is 4, time is 8, and C, which is the channels, is vocab size, or 65. And so we're just going to pluck out all those rows, arrange them in a B by T by C, and now we're going to interpret this as the logits, which are basically the scores for the next character in a sequence. And so what's happening here is we are predicting what comes next based on just the individual identity of a single token. And you can do that because, currently the tokens are not talking to each other, and they're not seeing any context except for they're just seeing themselves. So
just to check. So at this point, Andrej created a token embedding table, which is a two-dimensional table of dimension vocab size by vocab size. Okay. So if the vocab size in this case for this character level encoding is about 65. Let's reconnect. So it's 65 by 65, okay. And in the forward method, when we pass an index and the target over here, seems that we're only using the index, but we're not using the targets. And I don't see Andrej training the bigram model. He created I would have expected like a step to fit transform this model based on the data or something like that. Maybe I missed out something. So I'll backtrack a little bit and see if I missed out any information.
It's the bigram language model. So I'm importing the PyTorch NN module for reproducibility. And then here I'm constructing a bigram language model, which is a subclass.
Yeah, another question that comes to mind is what's a logit? So if I recall, a logit is a logarithmic probability, I guess. So it's like a log of the probability. What is a logit? So it's a log probability. So it's probability of something happening versus with respect to corresponding odds. Okay. So what's the meaning of logit? Okay, so it has a graph like this. Okay, like this. And it seems that if we pass in a very negative number, then if you pass in P, where P is a probability from, let's say, I guess it goes from 0 to 1, I guess. Okay. Okay, I'm guessing that this is okay, this is not very helpful. I think I'm probably having an incorrect chain of thought here. So let's quickly check what a logit is. So a logit function known as a log odds function is a function that represents probability values from 0 to 1. Okay, so this gives us a probability from 0 to 1, which makes sense. So in the sense, like when we pass in an index for a given, I guess for a word, like if you pass in a word, the index of the word would be a certain number, and we pass it into the embedding table and we get a row. So the logits in this case represents the probability of having other words given a word. Okay, that makes sense. It's like a bigram. So the row represents the probability of the next of a given word, like for a given word in a column to appear if we are given like the word index over here. So okay. But one thing that confuses me is over here, like the probabilities of a word given the next word is probably learned. So we probably have to train this model to understand the probabilities for the next word to come given a word. So let's see if Andre explains this.
Okay, so now that we have our batch of input that we'd like to feed into a transformer, let's start basically feeding this into neural networks. Now, we're going to start off with the simplest possible neural network, which in the case of language modeling, in my opinion, is the bigram language model. And we've covered the bigram language model in my Make More series in a lot of depth. And so here I'm going to sort of go faster, and let's just implement the PyTorch module directly that implements the bigram language model. So I'm importing the PyTorch NN module for reproducibility. And then here I'm constructing a bigram language model, which is a subclass of NN module. And then I'm calling it, and I'm passing it the inputs and the targets. And I'm just printing. Now, when the inputs and targets come here, you see that I'm just taking the index, the inputs x here, which I renamed to idx, and I'm just passing them into this token embedding table. So what's going on here is that here in the constructor, we are creating a token embedding table, and it is of size vocab size by vocab size. And we're using nn.embedding, which is a very thin wrapper around basically a tensor of shape vocab size by vocab size. And what's happening here is that when we pass idx here, every single integer in our input is going to refer to this embedding table and is going to pluck out a row of that embedding table corresponding to its index. So 24 here will go into the embedding table and will pluck out the 24th row. And then 43 will go here and pluck out the 43rd row, etc. And then PyTorch is going to arrange all of this into a batch by time by channel tensor. In this case, batch is 4, time is 8, and C, which is the channels, is vocab size, or 65. And so we're just going to pluck out all those rows, arrange them in a B by T by C, and now we're going to interpret this as the logits, which are basically the scores for the next character in a sequence. And so what's happening here is we are predicting what comes next based on just the individual identity of a single token. And you can do that because, currently the tokens are not talking to each other and they're not seeing any context except for they're just seeing themselves. So I'm a token number 5, and then I can actually make pretty decent predictions about what comes next just by knowing that I'm token 5, because some characters follow other characters in typical scenarios. So we saw a lot of this in a lot more depth in the Make More series. And here, if I just run this, then we currently get the predictions, the scores, the logits for every one of the 4 by 8 positions. Now that we've made predictions about what comes next, we'd like to evaluate the loss function.
Okay. It's a wrapper. Oh. Something is amiss. Or maybe it's because previously I had the impression that index is a scalar and targets is, I'm not sure what targets is. So let's try to demystify this. I have a feeling that I'm missing a few prerequisites here. Specifically the prerequisite here is what's the dimension of index and targets, and why is it that when you pass in an index you get a 3-dimensional array over here. So previously I had the assumption that this embedding here is of 2 by 2 dimensions. So if you pass in a scalar into a 2-dimension, you would have expected a 1-dimensional vector. But instead we are getting logits as a 3-dimensional vector. So what this means is my current assumptions for what's going on is wrong. Specifically my assumption that index is a scalar perhaps. And there's some details that I'm missing here that I'm not exactly sure what I'm missing. So let's go back, take a look at the type signatures of XB, YB, and that gives us a better understanding of what this forward method really does. So let's take a step back, let's pause, and let's take a look at this again. So get batch gives back a torch tensor, and as we mentioned, like okay, thank goodness we touched this before, it's just that I'm probably rusty. But XB over here is a torch tensor because get batch returns back a tuple of two tensors, and YB is also a torch tensor. But the thing is, this type hint doesn't tell us what's the dimension of the tensor. Is there a way to give the type hint? Type hint torch tensor dimensions. There should be a way to do that. Okay. No, I guess this is yeah, looks like there are third-party libraries that support the dimensions of the tensor, but for the sake of this video, let's not add that in. That's one additional prerequisite that's not very important. So let's see. Okay, so x over here is okay, so this is a one-dimensional vector, and this is two dimensions. So x over here is two dimensions, and xb represents the batch of x, and tb in this case, oh sorry, is yb, and yb in this case is the training batch here. So this consists of a batch of sequence, so that's two dimensions. So xb and yb is two dimensions. So in this case, we have this here. Vocabulary size would be an integer, and embedding table here would be two dimensions. The forward in this case takes in an index, but as we see, we pass in xb as a two-dimensional vector, so this would be two-dimensional. So idx is, oh, okay, nice. So Andrej actually gave like the dimensions here in the Python notebook already. So the first dimension is the batch, and the second dimension is the t. So t in this case is the size of the chunk, if I'm not mistaken. So let's, oh sorry, the block size. So t is the block size. So b is batch size, and t is the block size. Okay, nice. So if you pass in a batch size and a block size into a two-dimensional embedding, I guess this embedding class is smart enough to pass in every single value into this two-dimensional table. So this two-dimensional table becomes a three-dimensional table. Okay, that makes sense. If you pass in a scalar into a two-dimensional table, you get a one-dimensional table. If you pass in a one-dimensional table into a two-dimensional table, you will take every single number in the one-dimensional table to get a scalar into a two-dimensional table will give you a one-dimensional table. So in this case, since we are passing every single value in this two-dimensional torch tensor into this two-dimensional table, we get a three-dimensional table. So that makes sense. So BT, and we get C. Okay, that makes sense now to me. How about targets? Okay, I guess I'll leave it to Andrej to mention that next. So this makes sense to me thus far. Okay, nice.
And so in Make More series, we saw that a good way to measure a loss or like a quality of the predictions is to use the negative log likelihood loss, which is also implemented in PyTorch under the name cross entropy. So what we'd like to do here is loss is the cross entropy.
Okay, so the logits are the current predictions from the bigram model, and the targets is the actual probabilities that we expect in our training example. So the cross entropy is a loss function that pretty much gives a very high number if the logit is, let's say, 0 and a given number in logit is, let's say, probability 0 and the target is 1. Then the cross entropy will give a very high number. But if logits and target are the same number, let's say both are 1, then the cross entropy loss function here will give a very small number. So if you wish, cross entropy by itself is a prerequisite by itself. So I would recommend going online to take a look if you are not sure of this yet. So let's continue.
On the predictions and the targets. And so this measures the quality of the logits with respect to the targets. In other words, we have the identity of the next character. So how well are we predicting the next character based on the logits? And intuitively, the correct dimension of logits, depending on whatever the target is, should have a very high number. And all the other dimensions should be very low number, right? Now, the issue is that this is what we want. We want to basically output the logits and the loss. This is what we want, but unfortunately, this won't actually run. We get an error message. But intuitively, we want to measure this. Now, when we go to the PyTorch cross-entropy documentation here, we're trying to call the cross-entropy in its functional form. So that means we don't have to create like a module for it. But here when we go to the documentation, you have to look into the details of how PyTorch expects these inputs. And basically the issue here is PyTorch expects, if you have multi-dimensional input, which we do because we have a b by t by c tensor, then it actually really wants the channels to be the second dimension here. So if you, so basically it wants a b by c by t instead of a b by t by c. And so it's just the details of how PyTorch treats these kinds of inputs. And so we don't actually want to deal with that. So what we're going to do instead is we need to basically reshape our logits. So here's what I like to do. I like to basically give names to the dimensions. So logits.shape is b by t by c and unpack those numbers. And then let's say that logits equals logits.view. And we want it to be a b times t by c. So just a two-dimensional array, right? So we're going to take all of these positions here, and we're going to stretch them out in a one-dimensional sequence and preserve the channel dimension as the second dimension. So we're just kind of like stretching out the array so it's two-dimensional, and in that case, it's going to better conform to what PyTorch sort of expects in its dimensions.
I've never seen view before, and personally I didn't know that Torch actually has a functional module here. So they leave the helper functions in individual functions instead of encapsulating them under classes. So okay, I think I learned two things today. First is I didn't know that logits.view allows us to reshape a Torch tensor into this format. And I was personally quite surprised because I was initially expecting us to reshape logits into b by c by t, but Andrej chose to flatten b and t together into a single dimension. Okay, I don't think I fully understand that yet, but let's quickly take a look at the logits. Okay, neural network embedding. So what's the type of logits then? If you pass in something, if you pass in a tensor into an embedding. Okay, so let's go to our stuff here. Okay, actually no, it's okay, we can just use this. So let's do this. Run the same class that Andrej came up with. Vocab size is not defined. I guess because I haven't loaded everything from scratch, so I'm missing that vocabulary size variable. So yeah, here we are. I was missing this, and this is really a list of a string, I guess. Okay, and okay, type is not subscript. Type object is not subscriptable. What is this? Not Python 3.9? Okay, let's quickly check. Ah, 3.8. That explains it. Okay, guess we have to suck it up and use typing here then. I digress. Let's continue. Okay. Nice. I don't think I have to load this stuff, but let's just load it anyway to be sure. So we have this. Oh yes, of course, from typing import tuple. Because we're using Python 3.8 at the moment, so we have to use the typing library instead of using the class itself. So xp, okay, here we are. This should work now. Vocab size is not defined. Hey man, didn't we just load it above? Okay, let's vocab size is, oh, because I didn't run it. Nice. Okay, I got it. I got the vocab size variable. Now let's try this again. Okay, this works. And now we have the logits and the loss. Let me print out the type of logits. As well as the type of loss. Okay, nice. Okay, I was expecting this to be a torch tensor as well, so my hypothesis was thankfully right. And it looks like our forward method is calling forward. Sorry, our forward method over here returns back a torch tensor. And logits in this case is of dimension. Okay, we print out the logits shape here. Okay, let's print out the loss shape as well. So logits is of 2 dimensions, so it's of 2 dimensions like this, and the first is b times t, so b equals to b by t by c. Okay, so b is equals to 4, t is equals to 8, that's why I get 32, and c, our channel size, which is the vocabulary size, in this case is 65, and our loss in this case is, oh, empty. Is it because we didn't pass in any? No, we did pass in targets. So how did they use the targets? Okay, so this is also a torch tensor, but since it's none here, for some reason the type hint here is none. So it looks like this could be optional. Under what conditions would you want targets to be none though? I guess if you want to not use it for training. Okay, I guess that makes sense. When you are using inference, in sense you want to use the model to predict the next word, and you're not using it for training, then I guess the targets here would be optional. And we only pass it during training. Nice. Okay, so this makes sense. And okay, looks fine.
Now we have to do the same to targets, because currently targets are of shape b by t, and we want it to be just b times t, so one-dimensional. Now, alternatively, you could always still just do -1, because PyTorch will guess what this should be if you want to lay it out, but let me just be explicit and say b times t. Once we've reshaped this, it will match the cross-entropy case, and then we should be able to evaluate our loss. Okay, so that ran now, and we can do loss. And so currently we see that the loss is 4.87. Now, because we have 65 possible vocabulary elements, we can actually guess at what the loss should be. And in particular, we covered negative log likelihood in a lot of detail. We are expecting log, or ln, of 1 over 65 and negative of that. So we're expecting the loss to be about 4.117, but we're getting 4.87. And so that's telling us that the initial predictions are not super diffuse.
Yeah, this is new, but I did not know that we can actually do this. Okay, wow, okay, I didn't know we can actually use the Finder to do quick searches. Okay, and I'm pretty surprised that they flatten the targets. Okay, I mean, makes sense. I mean, logits and targets should be similar in dimension. Huh, okay. What does view exactly does? I'm a little confused. Like, targets is... Okay. Index and target are both BT. And we pass in the index into the token embedding table, but we didn't do that for the targets. So what exactly is the function signature of targets.view? And targets in the case is a torch tensor. So view is a method under torch tensor. So let's take a look at torch tensor view. Okay, returns a new tensor with the same data as self but of a different shape. So shares the same data, must have the same number of elements, but may have a different size. So for a tensor to be viewed, the new view size must be compatible. So okay, the size must be the same. Sorry, or rather the number of elements in the tensor before and after reshaping must be the same. I was wondering what's the difference between view and reshape over here. So it looks like shape does call view, then what's the difference between shape and view then? Let's do a quick Google. Difference between shape and view in PyTorch. The answers don't look very convincing, but okay. Okay, so you're saying that reshape may return a copy of a view of the original tensor, and view returns a view. But what's the difference between copy and view then? Okay, what's the difference between that? PyTorch view vs copy. Okay, so view is like a... Oh, view is view is a shallow copy, I guess, and a copy is a deep copy. PyTorch view is a shallow copy. Okay. Okay, but I'm not fully convinced, but it's okay. I guess we can continue the investigation between view and copy later. Let's continue with Andrej's explanation on the forward method.
They've got a little bit of entropy, and so we're guessing wrong. Yes, but actually we are able to evaluate the loss. Okay, so now that we can evaluate the quality of the model on some data, we'd like to also be able to generate from the model. So let's do the generation. Now I'm going to go again a little bit faster here because I covered all of this already in the previous videos. So here's a generate function for the model. So we take the same kind of input, IDX here. And basically, this is the current context of some characters in some batch. So it's also b by t, and the job of generate is to basically take this b by t and extend it to be b by t plus 1, plus 2, plus 3, and so it's just basically, it continues the generation in all the batch dimensions in the time dimension. So that's its job, and it will do that for max new tokens. So you can see here on the bottom, there's going to be some stuff here, but on the bottom, whatever is predicted is concatenated on top of the previous IDX along the first dimension, which is the time dimension, to create a b by t plus 1. So that becomes the new IDX. So the job of generate is to take a b by t and make it a b by t plus 1, plus 2, plus 3, as many as we want max new tokens. So this is the generation from the model. Now, inside the generation, what are we doing? We're taking the current indices, we're getting the predictions. So we get, those are in the logits. And then the loss here is going to be ignored because we're not using that, and we have no targets that are sort of ground truth targets that we're going to be comparing with. Then once we get the logits, we are only focusing on the last step. So instead of a b by t by c, we're going to pluck out the -1, the last element in the time dimension, because those are the predictions for what comes next. So that gives us the logits, which we then convert to probabilities via softmax. And then we use torch.multinomial to sample from those probabilities. And we ask PyTorch to give us one sample. And so IDX next will become a b by 1, because in each one of the batch dimensions, we're going to have a single prediction for what comes next. So this num samples equals 1 will make this be a 1. And then we're going to take those integers that come from the sampling process, according to the probability distribution given here, and those integers just get concatenated on top of the current sort of like running stream of integers. And this gives us a b by t plus 1.
There's a lot of moving parts here. 1, 2, 3, 4, 5. There's 5 moving parts. And let's try to break it down now. So IDX in this case is a two-dimensional array, two-dimensional tensor, and max new tokens is an integer. And let's try to understand this function signature better. Okay, so this is a two-dimensional tensor for IDX, and for each of the range in the max new tokens, like you are you are generating up to max new tokens, I guess. So if you pass in 100 here, then you're going to do this 100 times. And for each time, it seems that we are generating one additional word at the back. So IDX in this case represents a batch of block size. So the block size, let's say T is 8. So logits and loss, like doing this on IDX calls the forward method here. And in this case, the difference is over here, we don't pass in the targets because we are generating something. So generate is used to call the model to generate words, and that's under the assumption that it's already trained and you're using it to generate the next word. So logits in this case would be two dimensions, and loss in this case would be one dimension from what we see. Sorry, it's a scalar. So this is I guess it's worth doing this scalar, and what this means is logits is 2D, and specifically it's B times T followed by C, where B is the batch size, T is the block size, and C is the channel size or vocabulary size. And loss in this case is scalar, and this is in the case is none because there's no loss calculated over here. So we do logits equals to slice comes BC. Okay. I did not know you can slice a two-dimensional array like this. That's interesting. Okay, just to be sure, I'm just going to print out the dimensions of logits before slicing. Logits shape before slicing. So this would be logits.shape. And this will be logits after slicing. Let's try running this. Okay, this is long because we generate multiple times, but before slicing it was 1165. Okay, in this case, generate gives a torch tensor of 2 dimensions, but it's a 2D array, but it only contains really one item. So you are passing in, okay, sure. And before slicing it was here. It was 1165. And after slicing it was 1265. Okay. So it looks like we are so the initial T is 1, initial B is 1, and T is 1 in this case. So we are increasing the block size every time we generate. So how we do this is we slice this torch tensor. How does this slicing increase the size by 1 though? I don't think I really get this. I would have expected this operation here to increase the size to 1, 2. Oh, sorry. Sorry, I copied the wrong one. This is the one. This is the shape after slicing. Okay. So we are removing the third dimension, are we? Sorry, second dimension, are we? So we are changing this from becomes BC. Before it was before this was 1165 and this becomes 165. Now my next question is was it B that got sliced, or was it Since Andre commented this to be B, I guess the T got sliced in this case. So B time, it was initially BC after, before, BTC, after becomes BC. So T got sliced out. T got sliced out. But why? Why would Andre slice out T? And afterwards, he performed the softmax of logits to get the probabilities of all the... to get the probabilities of the words. So this BC, this BTC, and this is a torch tensor as well. This is a torch tensor as well. And IDX torch multinomial, they pass this probability into this multinomial thing here, and they sampled from the distribution. As in, they sampled from the probability distribution, I guess. Let's quickly take a look at the torch multinomial function signature. And over here, it returns a tensor where each row contains number samples sampled from the multinomial probability distribution. So that went from BC to B1. So we have up to C probabilities, and we sampled one from the probability, and we use the probability in the multinomial. Okay, so you're choosing one from the channel size. You're choosing the next character from this C based on the softmax probabilities. Okay, so IDX next is the batch of words itself after you choose from the distribution. Let's quickly check what's the multinomial probability distribution, like how does that look like, the shape. Okay, it looks, I don't think, okay, I guess is multinomial distribution the Gaussian? Is used when you have a finite number of classes or groups where the ordering does not matter. Yeah, that makes sense, because we are using the multinomial distribution because we have a finite number of classes where the classes represents our vocabulary size, and the ordering in the vocabulary size does not matter. Okay, and normal distribution is used for continuous data, values that theoretically take on infinite and are measured precisely enough. Which is, yeah, I guess that's why we don't use the normal distribution over the multinomial. That's why Andre decided to use multinomial here. I'm admittedly quite shaky on when exactly to use a certain distribution, but I think thanks to this tutorial, we don't have to wrangle with that. We can just build on top of Andre's intuitions and explore that later on. So in summary, we pass the index in this case, like the current input, which is a batch of size 1, and in that batch of size 1 we have one word token over there, and we call the forward method to get what are the next what are the probabilities of the next words. So we get the logics over here, the probabilities of the words, and in this case is B by C, which makes sense because for each of these batches, like for each of these words in the batch, we want the probabilities of the other words in the vocabulary. So we get this B by T by C, I guess. Then we remove the block size. We focus on only the last time step. That makes sense. We want to get the probabilities for the last time step to generate the next one because it's a bigram model. Okay, and we apply the softmax to get the probability. So we softmax the logits to get the probabilities across for each of the word. And using these probabilities, we sample one of these vocabularies by chance and we get the next word. And we concatenate the current tensor, the current two-dimensional tensor with the next word, and we get B by T1, and we continue the loop. Okay, I think I understand this now. Yeah, it's a humbling moment where when we encounter a code sample, it takes some time for us to understand what's going on, and that's certainly the case for me. So that was how I tried to demystify Andrej's generate function. So with that, now we know that the generate function is really calculating the logits for the next word token based on the previous word token and sampling the next word from the multinomial probability distribution. We can move on.
And then we can return that. Now, one thing here is, you see how I'm calling self of idx, which will end up going to the forward function. I'm not providing any targets. So currently this would give an error because targets is sort of like not given. So targets has to be optional. So targets is none by default. And then if targets is none, then there's no loss to create. So it's just loss is none. But else, all of this happens and we can create a loss. So this will make it so if we have the targets, we provide them and get a loss. If we have no targets, we'll just get the logits. So this here will generate from the model. And let's take that for a ride now. Oops. So I have another code chunk here, which will generate for the model, from the model. And okay, this is kind of crazy. So maybe let me let me break this down. So these are the IDX, right? I'm creating a batch will be just one, time will be just one. So I'm creating a little 1-by-1 tensor, and it's holding a 0. And the D type, the data type is integer. So 0 is going to be how we kick off the generation. And remember that 0 is the element standing for a new line character. So it's kind of like a reasonable thing to feed in as the very first character in a sequence to be the new line. So it's going to be IDX, which we're going to feed in here. Then we're going to ask for 100 tokens. And then n.generate will continue that. Now, because generate works on the level of batches, we then have to index into the 0th row to basically unblock the single batch dimension that exists. And then that gives us a time steps, just a one-dimensional array of all the indices, which we will convert to simple Python list from PyTorch tensor, so that can feed into our decode function and convert those integers into text. So let me bring this back, and we're generating 100 tokens. Let's run. And here's the generation that we achieved. So obviously it's garbage, and the reason it's garbage is because this is a totally random model. So next up, we're going to want to train this model. Now, one more
Okay, at least we got our assumption right. Our assumption was that Andrej missed out the training step on purpose. So, yeah, it's nice to know that our assumption was right. Okay, so let's run this and let's see if we generate gibberish as well. Yes, we did. So we generated gibberish here. I was also not thinking about the token, the new line token here as well. So I did not know that 0 actually represents the new line character over here. So okay, that's a pretty decent checkpoint that we have here thus far. So that's it for this video. It was a pretty short time step. We went from 22 minutes to just before training the bigram model, but I guess that was quite a lot of information here, so I think we understood this pretty decently. So that's it for this video. We will continue in the next video to understand the training of the bigram model as well as the subsequent chain of thought that Andrej will bring us through. So with that, see you in the next video.